שלום, אני המנהל מכירות של פתרונות בנטלי במקיט מערכות. מקיט מערכות קיימת אז שנת 85, אנחנו נציגים בארץ של שתי חברות עיקריות, של בנטלי סיסטמס ושל סימנס PLM. מי שלא מכיר, סימנס PLM זה כל הנושא של הנדסה מכנית, NX, Solid Edge וכו', שם בעיקר אנחנו עובדים עם חברות התעשייתיות הביטחוניות הגדולות בארץ, וכל התחום של בנטלי, מדובר בעצם על בנייה ותשתיות, הנדסה אזרחית, וזה בעצם העולם שאנחנו עוסקים בו. היום אנחנו בארץ עוסקים עם כמה תחומים עיקריים. התחום הראשון שאנחנו עובדים בו זה תחום של חברות מדידה, שאנחנו עובדים איתם מאוד צמוד, עם פתרון שנקרא Context Capture, למעשה פתרון שמאפשר לנו לעשות מודלים מש, רשת מתמונות ממטוסים, רחפנים, אפילו מסריקות לייזר, לצורך בעצם מטרות מדידה ותכנון על גבי המודלים האלה. זה תחום אחד שאנחנו מאוד מובילים בו. תחום נוסף שהוא מאוד פעיל אצלנו הוא תחום של המים. טוב,
משהו מתכננים מים, משתמשים בתוכנה שלנו.
מתכננים מים, אוקיי, אז זה לא היה מזמן, זה כבר טוב. אז פעילות נוספת, כמו שאמרתי, פעילות של תחום המים, שאנחנו מאוד פעילים עם כל מתכנני המים בארץ, שעובדים עם כלים של בנטלי בתחום התכנון. ופעילות נוספת כמובן שאנחנו עוסקים איתכם, כל נושא של פלקסיס, הנדסת קרקע וביסוס, שזה פעילות שבנטלי רכשה לפני כשנתיים, ומאז הם בעצם חלק מבנטלי. וזהו, אנחנו שמחים כמובן שאנחנו עובדים עם השוק הזה, אנחנו רואים פה יכולות ודברים מאוד יפים. והמטרה היום של הסמינר היא להביא קצת יותר לפרונט את הפלקסיס 3D, עבור כאלה שעובדים גם עם ה-2D וגם עבור לקוחות שלא עובדים עם הכלים, קצת להבין מה הכלים האלה יכולים לתת לנו, וזה שכמובן ג'וזפה יציג את עצמו, יעבור קצת על היכולות של הפתרון, על המודולים הנוספים שמגיעים עם הפתרון, וכמובן מספר פרויקטים ומודלים שהוא יוכל להראות לכם בתחום הזה. אז נעבור לג'וזפה. Giuseppe, you can start your...
Okay, thank you.
Great.
So, just I share my screen. Is this? Sorry, I have problem in sharing. Okay. Can you see?
Yes, Giuseppe, we can see it.
Okay, perfect. So, good morning, good afternoon, actually, everybody. Thank you for being here today. My name is Giuseppe Cammarata, and I'm a research product manager for Plaxis product in Bentley Systems in Italy. Before joining Plaxis in the Netherlands, I gained academic and professional experiences in Italy, Switzerland, and Canada, working for engineering and consulting firms. In this presentation today, I'm going to talk about Plaxis 3D analysis for geotechnical engineering design. The outline of my presentation is as follows. After a short introduction to Bentley and Plaxis, I will provide a general overview of the key strengths of Plaxis 3D along with its advanced capabilities, and start to discuss the reason for adopting 3D in design analysis. For a better understanding, I will then show the peculiar aspects addressing the modeling of 3D for several engineering market sectors, showing also some model examples. Bentley's mission is to provide is a global provider of software solution whose mission is to provide innovative software and services for the enterprises and professionals who design, build, and operate the world's infrastructure, sustaining the global economy and environment for improved quality of life. Geotechnical engineering software was the missing link in Bentley's comprehensive software portfolio. So this led Bentley in 2018 to acquire Plaxis, which is the world market leader in geotechnical engineering software. As you might already know, Plaxis is a finite element software for geotechnical design and analysis aimed at simulating soil and rock behavior and taking soil and rock structure interaction into account. As advanced modeling tool, Plaxis allows for a more realistic modeling where risk is better understood and reliability is increased, which all lead to more accurate analysis and designs, which can lead to large cost savings. So what are the features of a modeling software such as Plaxis that make it an efficient tool? The modeling approach, it has to be user-friendly with an intuitive workflow, but at the same time, the results of the calculation have to be reliable and thus based on robust developments and implementations. Because of geotechnical engineering deals with natural and complex materials, their behavior has to be accurately described through the most appropriate constitutive law. So a comprehensive library of material model is of paramount importance for benefit from advanced modeling. In addition, as anticipated, the soil-structure interaction is crucial, and thus there is a need for proper structural elements simulation within the geotechnical framework. And all of these associated with the possibility for the operator to display a comprehensive set of detailed results. Finally, the tool has to be usable in every project stage. As anticipated, Plaxis provides a user-friendly and intuitive workflow based on modes. There are 5 modes: the soil mode, where the soil conditions are defined; the structure mode, where structures and loads are created. The geometry is modeled via predefined structural element types and loading types using CAD-like drawing tools, leading to fast and efficient finite element model creation. It is also included a special tunnel designer tool that we will see later to quickly create and edit tunnel cross-section and loading conditions. The third mode is the mesh mode, where intersection and mesh preparations are done. The mesh is automatic, and there is the possibility for the user to manually refine it. Then we have the water levels mode, where hydraulic conditions are defined, and finally the stage construction mode that allows users to accurately model the construction process by activating and deactivating soil clusters and structural elements in each calculation phase. For geotechnical simulation, the adoption of the most suitable constitutive law is crucial for the reliability of the results. And within this framework, Plaxis offers a comprehensive library of models for both soils and rock masses. In addition to standard model, it offers a set of user-defined soil model programmed in Fortran and compiled as DLL, and provide also the possibility to add UDSMs developed directly by the user. Thanks to the soil test facilities in Plaxis, the user can carry out comparison of the behavior as defined by soil model based on the entered set of soil or rock parameters with the results of laboratory and site investigation. This very useful tool is aimed at the optimization of model parameters such that best fit is obtained between the model results and the test data. In addition, as said before, the soil structure interaction is crucial, and thus there is need for proper structural element simulation. And with this regard, Plaxis offers a wide range of different structural elements that can be easily used for any engineering application. To all of what showed so far, Plaxis provides powerful post-processing through the versatile output program, which offers various ways to display forces, displacement, stresses, and flow data shown in contour, vector, and isosurface plots. Cross-section can also be displayed, and graph created allowing a detailed inspection of the results. Let's now have a look at Plaxis' advanced capabilities. And let's start from the groundwater flow, which is an important issue in many engineering fields such as geotechnical, environmental, and hydrological engineering. With this advanced feature, users have the possibility of considering transient flow, performing different type of calculation where the interference between the flow field and the strain field can be taken into account up to the level of fully coupled analysis. In addition, Plaxis offers various predefined properties to define the unsaturated soil behavior. Moreover, the user can also assign time-dependent variation of water levels or flux to model boundaries, as well as to simulate various complex hydrological conditions. Application would be, for example, excavation and mine dewatering, analysis of rapid drawdown, the effect of rain or flooding on, for example, slope stability, and drainage system and pumping test. Plaxis has state-of-the-art capabilities for dynamic calculation. Dynamic problems may involve two different types of situation. In the first place, these are induced vibration, which can be caused by traffic, such as trains, trucks, by machines, for example, generators and wind turbines, or construction work, such as drilling and blasting. In the second place, there are earthquakes as a result of tectonic movement. The major dynamic capabilities of Plaxis include the advanced constitutive model UBC 3D PLM, which deals with the cyclic loading, strain and pressure accumulation and liquefaction. Plaxis also enables the users to simulate the coupling between soil deformations and transient seepage in the dynamic loading phase with the advanced calculation type dynamic with consolidation. Using this calculation type offers generally improved stress prediction and accounts for both eventualities of accumulation and dissipation of excess pressure during earthquakes. In addition, users can also perform dynamic calculations with the updated mesh setting in order to account for large displacement, which may occur, for example, in case of liquefaction. Other features required for dynamic analysis involve the boundary condition. Special boundary conditions are in fact needed to absorb waves at the model boundaries, avoiding reflection which would disturb the results. Besides the static loads, user can define dynamic components of loads by means of the so-called dynamic multiplier, which also enables to define signals as linear, harmonic, or defined through a table, and also to scale the signal itself. A special feature that we have implemented is sorry, I'm trying to start this short video, is the moving loads. This feature is only available in Plaxis 3D, and moving loads are defined by assigning a movement function to static loads that move along a predefined path. The investigation of dynamic issues from a geotechnical engineering perspective may involve several types of analysis. Example of application would be dynamic soil structure interaction analysis, which provides input for structural engineers to design buildings and other structures. Stability analysis under earthquake conditions is generally required for the design of any infrastructures in earthquake-sensitive areas, and there are also situations where the stability under dynamic loading due to vibration is required. It's also important to assess the risk that liquefaction occurs and the consequences for the structures involved in terms of deformability and stability. Advanced thermal analysis is necessary when the effects of heat flow on the hydraulic and the mechanical behavior of soils and structures need to be taken into account. In the current version of the software, the models is available in 2D only, but will be available in 3D in one of the next release. And because of that, I will not spend more words on this feature for the moment. So let's discuss now the reason for adopting 3D in design analysis by answering two classical questions may be asked. Do I really need a 3D model? And what if I use a 2D model in any case? Actually, only very few projects can really be considered 2D, and most projects have 3D effects. So modeling projects in 2D would mean that one forgets something, since it's hard to estimate whether omitting 3D effects is conservative or not. Generally, this is covered in applying all kinds of partial factors. This means that very often a 2D design is over-designed in order to cover the uncertainties of a 2D model for our 3D world. In a 3D model, those extra factors are not needed, and thus modeling can be more cost-efficient than 2D. Let's try to better explain this with a very simple example sketched in this slide. Let's have a look at a typical situation where an excavation adjacent to an existing building has to be executed. We will have to consider the effect of construction equipment, such as heavy excavator, defined as working loads, on the stability of the excavation, and the effect of the excavation on the adjacent existing building. If we decide to carry out the analysis with a 2D model, we will select a cross-section, very likely the one that I draw here, which intersect both the working load, the excavation, and the existing building. And by doing this, we'll accept to stand with the assumption of line strain model here reported. So one dimension is relatively long. There is similar geometry and stress or loading condition in any cross-section perpendicular to the long dimension. No strain perpendicularly to the long dimension. No shear stress and arching perpendicularly to this dimension. And model represents one length unit out of the plane. It should thus be clear that by performing a 2D plane strain of the situation presented initially, we are actually considering a 3D representation which cannot be considered as representative of the real one. So 2D plane strain conditions, in fact, generally comply with the analysis for linear civil infrastructure, such as those represented in the left hence figure, but surely not to the one represented in the figure in the right side of the slide. Let's now show the peculiar aspects addressing the modeling to 3D rather than 2D for several markets sector of the civil engineering. The first is concerning with the foundation and excavation, which thus includes both shallow, deep and deep foundation, excavation, and a combination of the previous. The first aspect that we have already previously considered and which might occur in any engineering project is the geometrical aspect, which include also complex situation, such as the one showed in the slide where 10 basements level are to be designed on a steep slope side. High cost value of traditional methods for stabilization of excavation pit encouraged engineers to study more about soil characteristic and its application. Arching effect is one of these characteristics that occurs in many geotechnical engineering problems, but does not always receive the deserved attention. In fact, allows to provide safety and economy of project by optimizing the use of resources in the construction of discontinuous retaining structures. When one is dealing with pile design, it is important to consider the behavior of the pile group. And for doing this, in Plaxis, user can use the special embedded pile structural elements. There is also the possibility of simulating piles as volume elements, as the one represented in blue here. But of course, there are problem when you want to simulate a pile group, because you will start to have lots of elements in, which will be demanding in terms of calculation, but with also the possibility to have bad element shapes of the finite element mesh. And for that, the embedded pile, respect of this volume pile, allows to simulate a large number of piles by taking into account all the peculiar behavior of piles. Settlements of adjacent building, and more in general the interaction with other infrastructure, is another common aspect that might be to assess in any geotechnical project, such as, for example, the one shown in the slide, where a deep excavation is planned in an urban area. If we, in addition, we consider that this area is in the Netherlands, we might understand how settlements can be important to be assessed in an accurate way. So before continuing with the presentation, I want to show you an example of an excavation in the vicinity of an existing building. Other than the sheet pile walls, the shoring systems is represented in the model, along with the different excavation level stages. I'll thus show how efficiently the visualization of the results can be used for assessing the influence of the excavation and the forces on the structural elements. Okay, so this is the model I was mentioning. Sorry. Okay, we start from the, as I mentioned before, I will go through fast through the different modes. So in soil modes, what has been defined in this already created model, it's the stratigraphy of the soil. This is done through the concept of creating boreholes, but the users can also import surfaces. Whilst in the structures, as you can see, all the soil layers are now somehow hidden of a certain percentage of transparency. So we can see all the structures elements that have been created. So here, for example, this is the excavation. Specifically, the brownish one are the interfaces that are represented parallel to the surface. As you can see, they are not attached but detached, just in terms of representation. So And so this is the excavation where we can see the different level of the excavation. These lateral are the sheet pile walls. As you can see here, these are defined as SPW, which stands for sheet pile walls. And we have for each level of the excavation, the shoring system installed. So we have, for example, struts simulated as node-to-node anchor, and wailings simulated as beam. We have piles of the existing building simulated as for embedded beam. In addition, as you can see here, there is this volume, which is not representing an excavation, but just a volume where we will then refine the mesh, because what we are interested in is especially the interaction between the excavation stages and the existing building. And so, as I will show you in the mesh mode, I will hide. So this portion, which is the volume between the excavation and the building, has been refined. So the refinement of the mesh is performed through the coarseness factor to which the users can enter the different values. And whenever Plaxis encounter structural elements, it will automatically increase the refinement of the mesh. So this value, for example, is 0.5. This has been by default given by Plaxis. Here instead, we acted independently from the automatic measure for assigning a very little coarseness factor, which means a very refined mesh. So then we move into the stage construction. So here in the stage construction, we start from an initial phase, which means the phase that will simulate the in situ field stress, which the original, the virgin in situ stress. So even before the realization of the building. So as you can see, the building is gray. When it's gray, means that all these elements are deactivated. So the next phase, it's the realization of the existing building. So as you can see now, it's colored. And this is considered our initial situation. So to not be confused with the initial phase. The initial phase represents the initial condition of the soil, and the existing the second one is the initial situation where we will also we will start from the situation where we are going to build the excavation. So now we look at the different phase for doing this and facilitate the visualization. I will hide the soils layer. So as you can see here, the these elements, so the wailings are gray, which means they are not active. So we start, the first step would be the sheet pile wall installation. We remove again the interface. Then we excavate, and we can see here the first 2 meters. And here, these elements are deactivated. The shoring systems is deactivated. This can also be assessed here because they are not flagged. So we then install the shoring system of the first level, which further excavate up to -6.5 meters. We install the shoring system for that level, and same for the next stages of excavation up to -14. So in this specific model, I move now in flow condition. So we have a global water level which is this one, this blue line represent the phreatic level. So we are also simulating the watering by, I show you, so when we start, all these element, all this volume that will be then excavated refers to the global level. The global level is this water level that is defined here. Global water level is the one defined through a borehole. If we go, we start excavating, I will select this specific volume. You will see that once this volume is excavated, for simulating the watering, conditions of dry condition are assigned to this volume, whilst the volume below heat are assigned with interpolate condition, which means that, so this is a feature that enables linear vertical distribution of the layer from the pressure in the boundary with the layer above to the pressure in the bound with the layer below to the current layer. So let's move to the stage construction again. So once we finalize the excavation, then we can start the calculation with this button. But of course, this model has been already calculated, so I will directly move into the output. So in the output, it takes a few seconds to get open. It's also a pretty large model. So first thing, you can see the mesh and how refined has been done in between the two structures. The first aspect I want to show you is, for example, we are interested for sure in the deformation, so in the total vertical displacement that occur between the two at the bottom of the excavation and between the two structures. So from here you can see you don't see lots of displacement. The biggest displacement are concentrated in the bottom. You can also hide volume, but the best way to visualize results can be cutting a vertical section. So here, and in this way you can analyze section by section and phase by phase, because you can move into the phase. Is updating, yeah. So this is the phase where I have just installed the sheet pile walls. Then when we excavate, we can also investigate the different section by clicking on Control plus and Control minus. So this section will move up and ward along the model. And something that we might be interested for assessing the impact of this excavation is investigating what is happening in the foundation piles. So we will select them by drawing a window, and we will select the embedded beams. Okay, so here I'm visualizing the embedded beam. So now I'm visualizing the vertical displacement, but it might be more interesting to visualize the horizontal displacement. And investigating them, okay, I will scale manually in a way that for sure we will have the same scale factor for all the conditions. So if I look into these piles, I can also investigate each single pile. We will see that from when just the existing building was constructed up to the finalization of the excavation, the condition of the piles have changed. Okay, so these aspects might be, I was actually, I concluded this part of the demo. So in this way, we can investigate what happened on the pile. So you can also visualize, but I will show with the next example, also the bending moment of these piles. And this way, the users can understanding and assessing the situation of the existing structures and the effect that the excavation is giving to it. Okay. I will now move back to the presentation. Okay. So, so let's continue now with presenting by having a look at the embankments and dams. So within this engineering sector, Plaxis has been successfully used for decades, performing design analysis of railways, roadways, water retention, and flood control mitigation works. So these are, as I already also mentioned, generally linear infrastructures that, as already mentioned, comply with assumptions of 2D plane strain condition. However, there might be the need for taking into account 3D in several cases. For example, when strong heterogeneity of the geological conditions is encountered, which in turn implies strong variability of the geological layers. Also in case of interaction with adjacent structures, and if the effect of moving loads needs to be considered. As previously anticipated, Plaxis 3D offers a special feature for simulating moving loads. So with this regard, I want to show you an interesting example captured in this short video that describes the usage of moving loads features for simulating the train passage over a railway embankments and its effect on a nearby buried pipe. So if you don't hear the volume, the audio, please let me know. Actually, it's not even starting. So I will. Let's see if this way. Please let me know if you don't hear the audio.
Giuseppe, we can see the video, but we can without audio.
Ah, okay. Okay, sorry. So maybe now you should be able.
So for our model here, we start with just soil layers. And of course, we construct the embankment, because that's of course where we will put the rails and sleepers on. So we zoom in, we can see also here modeled by beam elements and adding the moving load functionality here. So these are the loads of the carriages. And if we look at the load input, we see here that we have a special movement function, and this movement function actually shows we have a 35 meter per second train movement, which roughly will be 125 kilometers an hour or 80 miles per hour. Show the results for the deformed mesh, displacements, and actual forces in the rails, and we see here the train moving in the calculation. And you can see even after the train has passed, there's still some movement happening in the model. Now, second challenge that we have to do is that we add the existing infrastructure to the model. Same model, we use the special extrude functionality inside Plaxis to get a pipe below the newly constructed embankment. It's also activated here in our stage construction. We run the analysis, we see our deformed mesh, and if you look closely, you can see the effect of the pipe in the results, but also the movement of the pipe, which are scaled up, so they look bigger than they really are. And also here you can see that the pipe still moves after the train has passed.
Okay, so by talking about buried structure, so we now move into the underground works in 3D, and with this we refer to the design of deep and shallow tunnels along with underground mines and storage caverns and cavities. So we have broadly discussed geometrical aspects, and this also applies to underground works. A first example can deal with the requirements of considering the effect of intersecting tunnels, such as those shown in the figure. Another example is when the variation of tunnel cross-section occurs. So in this case, loft polycurves and blend surface features can be easily used to provide smooth transition between non-homogeneous sections. For tunneling, it is important to accurately simulate the construction process of the adopted excavation method, which is generally modeled by using the principle of convergence confinement method, which addresses a 2D plane strain problem of the ground support interaction. So the 3D effect is then considered through the fictitious pressure PF as represented in the picture in the bottom part of the slide, on the tunnel wall that decreases progressively over the excavation process. So the evolution of this fictitious pressure is characterized by the confinement rate, lambda, here, which depends on the distance z between the considered section and the tunnel face. So lambda value depends on many factors, so ground condition, length of unsupported section, advancement rate, and experience also. So on the other hand, and I hope now the video will start. No, I have to exit from the slideshow. Sorry, but it's the only way for running the video. I don't know why. So on the other hand, 3D allows to properly model the construction sequencing in terms of excavation phases, as shown here, by also differentiating the advancement of the front face from for crown and invert, and where advancement rate and length can be accurately simulated. So reliable modeling of construction sequences is also important for the reinforcement systems, such as, for example, when reinforcement is installed as represented in this video with a staggered pattern, or umbrella arc method is in use to increase the excavation front stability. And last but not for least, as a consequence of what said so far, the interaction with other existing reconstructions might require the accuracy that can be captured only with 3D model. So with this regard, I now move and show you another example of tunnel excavation planned in urban area. The design tunnel is in fact excavated in between two existing structures, and all the excavation stages along with the reinforcement system and the support with lining are simulated. Okay. Okay, so this is the model. I hope you can see it. So I'm not going through the different mode again. Just for the soil, I want to show you that here, for simulating these not horizontal layers, the concept of boreholes was used. So 3 boreholes were simulated, and they can be seen here. So we have 3 different boreholes where the stratigraphy has been defined with different depth, and this at the end will provide a non-horizontal layer. So then in the structures, we define all the structures that we will look at them later. So as you can see here, we have defined all the reinforcement and lining system. So how this was achieved? So for doing this, I'm referring to the tunnel. We used the tunnel designer tool, which is composed by 4 different modes. So in the cross section, we define the the outline of our section. In the properties, we define both the support as liners, so and as you can see here, so this has been simulated as shotcrete, and also in reinforcement, we have simulated the rock bolts and the umbrella arc. In trajectory, we define the direction of our tunnel. So in this case, it's just a line, but you can also you can imagine to have a curved trajectory. So you can also draw that. And here we defined also the slices, so which means the different stage of advancement of our tunnel. So we split the trajectory into certain amount of advancement of which will correspond to the slices of the construction stages, as we will see later. And we also define the sequencing of the construction of our tunnel. So so we will have 4 steps, and this 4 step will be looping through the construction of the tunnel. So the first is excavating the upper part of the tunnel. The step 2 is installing the reinforcements. Step 3 is the upper part of the liner installation, and finally we will excavate the invert and install the liner. So I will skip the mesh mode. So the concept is exactly the same we described before. So and as you can see, all the mesh concerning with the tunnels has been refined. So we can thus move into the stage construction. So for I will hide the soil so we can concentrate on the tunnel. So here, as you can see, we are in initial phase where everything is gray, also the existing building. So in phase one, we have the existing building above the tunnel, but everything regarding the tunnel is still not active, it's still deactivated. As you can see, all the umbrella and reinforcement is gray. You do not see any kind of excavation. And we start with phase two. So phase two is the first part of the excavation, which correspond to the step one in the sequencing we defined. So in the next phase, we will have that another section has been excavated. So this slide will follow the step one in the sequencing, whilst in the first slice, we are experiencing the step two. Then in phase four, we will experiencing here the step three, which means installation of the liner, here the step two, and here the step one of the sequencing we defined, and so on. So now in phase five, this will be excavated and the invert liner will be constructed. Here we will activate the reinforcement. Here we will have the upper portion of the liner. Look. And so this is the interface. I can hide the interface and so on. So this way, all interfaces. With all these faces, sorry for the interfaces that keep coming. So we define all the different construction stages. So let's now have a look to the output. Hopefully output will not crash again. If in case and I have not finished, I will restart again. So what I'm going to show you is the default plot when the output is open is the default mesh. So here you can see that it seems that it's collapsing, but it's just due to the scale. So we will change the scale and we will bring it to a more realistic one. Okay. So here you can investigate different. So we start from phase one. So you can investigate different kind of aspects in terms of deformation, stresses. You can create curves and export the information you plot on your output. So now let's start looking into the vertical displacement. Okay, so this is the condition, the initial situation. As soon as we start excavating the tunnel, we will see that the concentration of displacement will move in the zone around. So the bigger displacement will be in the zone around the tunnel that is getting constructed. So if we move to a more advanced phase, and we can also visualize from a 3D visualization that here the displacement will increase. So now it's plotted. And a good way for investigate the model is again to cut a vertical section. So if we create a vertical section here, and we view it in the front view. Okay, now we can clearly see what is happening. So for this phase, we can move up back and forth the section by inspecting what is happening. So I'm moving forward, and as you can see, the displacement are reduced because the tunnel has not been excavated in that direction yet. So it's just getting the effect of what has been excavated so far. So, and this can be done for any phase. So let's go into the last phase. As you will see that this displacement will increase for this specific section. And again, you can move. So this is the best way for visualizing how the section is moving. And something else I want to show you that unfortunately I didn't have possibility to go through too much before was the effect on the foundation. So we select again the foundations, embedded beam, select, enter. So here you can, for example, if we visualize the horizontal displacement and we put a scale which is the same for both of them, yeah, apply, okay. So you can see the effect of the excavation on the displacement of the piles, which in turns means that something, this tunnel is affecting might affect the stability of the foundation, and so this needs to be investigated. So as you can see here, by moving in on the excavation phases, we will see that displacement are increasing. You can also investigate the force into the the piles, like bending moment, and again going through the different phases. I forget in the previous example to show you also that bending moments can be visualized into the sheet pile walls. This is useful in order to understand what kind of force, and also to visualize the effect, the 3D effect due to the different corner that are characterizing the geometry of the excavation. Okay, so now going back to the presentation, there are just few couple of slides. Another sector where Plaxis 3D has been successfully adopted are oil and gas and offshore. So Plaxis can also be used, in fact, to perform settlements and bearing capacity for onshore infrastructure like petrochemical plants or LNG tanks, as well as offshore geotechniques. In offshore geotechniques, most of the problem benefit from the three-dimensional analysis as it fully captures the complex interplay between the soil and structures under various loading conditions and its effect on change in stresses and pore pressure. So Plaxis offers also several constitutive models dealing with undrained soil behavior, as already said, encountered typically in offshore engineering. Finally, there is also a special software called Plaxis Monopile Design, also Plaxis Modeto, which is specific tool introducing an enhanced design method for monopile foundation for offshore wind turbines. So Plaxis Modeto has been demonstrated that can lead to a high reduction in the amount of steel of each monopile, and as such in the overall cost of any wind farm. So thank you for your attention. So now we can move into the Q&A session.
Thank you, Giuseppe. חברים, מי שמעוניין לשאול שאלות, זה הזמן המתאים. תרגישו חופשי, בסדר, לפי, בכיבוד אחד של השני, בדיוק, ולשאול שאלות בשמחה. Giuseppe, we'll wait a few minutes if someone have questions. I told them this is the time to ask.
Sure.
תומר, אני רואה שאתה מנסה לדבר.
Yes, hello Giuseppe, hello guys.
Hello.
I'm Tomer from YSS company. I want to ask about the structural elements that you use at the Plaxis model.
Okay.
I mean, which options of structural elements do you have to model them?
So for which kind of, so which model are you referring to? Which model, the first of the second? You mean the one about the excavation of the tunnel?
Let's say of the tunnel. I mean to the building, the piles.
Oh, okay, yeah. So the building, I go back and I share my screen. So for the building, so this is, as you might understand, so this is a representation of the building in this specific model where we were mainly interested in seeing what was going to happen in the foundation. We could also have to simulate just the pile. So for the pile here on this model, I used, one second there. This hide. I used the embedded beam. It's here. So these are embedded beams.
Okay.
And I guess you want to know how they've been characterized. So for doing this here in the material set, so this window concerning with the materials can be visualized in each of the modes. Is actually the only button that you will see in all the modes. So here you characterize your materials. So, and this is the typical material set windows where you define the properties of your embedded beam. So the type of beam, so geometrical properties, as long as, sorry, mechanical properties, like for example, the axial skin resistance, which means the lateral resistance and the base resistance. So this, for example, for the piles, the liners here are, for example, simulated through plates. So if we go here and we move into the plates, you will see shotcrete. So shotcrete has been defined as a plate in the with elastic properties. So you just have E, nu, and G to be defined, but you can also define the plates with elastoplastic properties. So by also indicating the yielding stress. Now, it would be also more useful, I guess, moving into the other model. So if you wait, and this way I will also show you what I forgot to show all of you. It will take not long. Okay. For the sheet pile walls, we adopted, again, plates. So here, if we go and we look, so plates, so this is the sheet pile walls that have been used for simulating the sheet pile walls. Same as, for example, a plate was also used for simulating the concrete mat of the foundation of the building. So let's say that there are a certain amount of structural elements that are very flexible, and these can be applied to different situations. So other elements that were not, for example, adopted in the tunnel model are these. So these are the struts. The struts have been modeled as node-to-node anchors. So they are defined here, anchors. So these are the different struts that we defined. In this case, as elastic. Again, here you can simulate as elastoplastic and elastoplastic with residual strength. In addition, we have beams that we applied to, for example, the railings. Here, these are the. Now, if I remove the interface, I will be no, not the. So here, these are, for example, a beam which is representing the one of the railing around the surrounding the excavation.
Thank you.
You're welcome.
We have more questions for Giuseppe. Just a second. We have in the chat window a question from Doya. Are the dynamic loads option is in the advanced 3D program or in the basic?
Is in the advanced. Okay. The dynamic option or have not been part of the basic option for the suite, and I cannot expect that they will not be in the future as well. So dynamic is pretty advanced in terms of options. So it's not part of the basic Plaxis 3D.
Okay, thank you. Thank you.
I have another question, if it's okay.
Sure.
Okay. As my experience with software like that, I'm familiar with behavior of heaving, or you know, when you are trying to model a soft ground, so you need to choose the right failure criteria. And I know that it's hard for me to get all the right parameters to exactly to describe the
Oh, you muted. I think you got muted, so we cannot hear you anymore.
Sorry, now you can hear
no
me?
problem. Yes.
Okay, so I'm asking again about the when we are trying to deal with soft ground, so we have a behavior like heaving or something like that. And actually, the big problem is with the failure criteria, and we have problem to get all the parameters that we need if I want to use a hardening soil, let's say. So,
oh, okay. So your point is that so you already use Plaxis, I guess.
Not Plaxis, but I'm asking if there is a tools that Plaxis help us to get the right parameters that we need for this criteria.
Ah, okay. So actually, the best tool that is available in Plaxis, and am I still?
Yeah.
Sorry, am I
Yes.
still sharing my screen?
Yes.
Okay.
Yes. Yes.
Okay, so perfect. So I will bring this. I think it's actually the screen and not just the model. So it's the soil test facility. So this facility is actually aimed at helping the users to calibrate the parameters that has to be entered in the model in order to fit what are the available data that of the behavior of the specific soil. So the idea is, of course, if you have to start, I can understand if you have to select, if you have to enter our input for a material simulated as more Coulomb. So there is lots of experience in defining C and phi. Okay. Whenever you move into an advanced model like the hardening soil, you might start be skeptical, or because you need to enter some parameters that you might not have on your available. So ideally, you should have those available from any kind of data. So they can be lab, field. So, but for sure, what you can do is, if you have in mind how your material should behave, you can investigate the behavior of your material by running this soil test facility. Because whenever you are here, so here, this is hardening soil, you have defined all your parameters of your soil, and you move into the soil test facility, you can inspect in terms of behavior these parameters that you entered means. So you can simulate different type of test, including test in dynamic condition. So, and here you might investigate understanding whether what you are getting is fitting what you have in the reality, or at least fitting what, in your opinion, from your engineering judgment, the behavior would be for that specific soil. Am I answered your question?
Yeah.
So this facility is really, really, really powerful. So as you can see here, there are several kind of different tests that can be simulated with this facility. Of course, this is a run at the simulating a test. So this is not a finite element tool. So this is for calibrating the soil parameters.
Okay.
Against available data from investigation or engineering judgment from the professionals.
Thank you.
You're welcome.
Thank you.
Is there any other question?
יש למישהו עוד שאלות נוספות לפני שאנחנו מסיימים את הסמינר שלנו להיום?
So if...
Okay, I think we don't have more questions.
I do have a question, please.
Okay.
Sorry.
Go ahead, Daniel.
Yes, hello. Is there any rule of thumb for the number of lab tests you do for these sophisticated parameters?
Sorry, I cannot hear you very well. So I think there is. Can any other one that has the microphone on can mute it, please?
I'll write it down.
Okay. So can you say again? Very, 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 very.
Is there any rule of thumb for the amount?
The rule of thumb for
laboratory tests in order to determine these, let's call them sophisticated parameters.
Oh, okay. So,
or maybe can you get specific for the project that we're seeing? How many soil CU tests did took place there?
Okay, so this is a demonstration and it's not a real case actually. So this is to be clear. So the rule of thumbs usually comes with the experience. So unfortunately, is not our task to provide this kind of professional advices, because as you can imagine, so rule of thumbs depends on experience, and so these are strongly based on engineering judgment. But what I can tell you, so I'm not able on off top of my head to give you a specific rule of thumb for each parameters, but there are, of course, in the literature, authors that have investigated and provide some idea on how this material can be characterized. But of course, it depends by the specific soil conditions. So what eventually the professional can do is to look into the literature, scientific and technical, for finding similar condition to the one that apply to his site, and then using and trying to use those for the modeling. But this kind of advice goes completely beyond to what we actually provide, because we are we provide the tool, so the finite element tool for performing that, and we have the users has the possibility to enter the right parameters to properly characterize the soil with that advanced tool. But we do not provide rule of thumb parameters for the different this is you you will, I don't know if you use Plaxis or you will use, but this is the same in the manual. So the manual describes how the advanced constitutive law works, but never provide rule of thumbs. So this is up to the engineer. So it's based on engineering judgment. Unfortunately for you, I know.
Okay, thank you very much.
You're welcome.
Ron, I have a question, please.
Yeah, go ahead.
Yeah, like I'm from your experience, when you use the same case in 2D compared to 3D, without any non-similarity or things that are like the cases you showed, can you tell what is the difference in percentage, or maybe from your experience, if you take the same case with the same soil parameters and structure properties, does the 3D give any advantage? Let's say it's less conservative in some percentage that you can point at?
No, there is not a percentage that can be applied to all the different cases, because so just look at this. Let's imagine that this is just an excavation. You don't have the buildings. It's just an excavation, and not with this corner, because of course this corner was made just to further complicate. But let's imagine that this excavation is just a rectangular. Okay. So again, so the condition will be, so the difference between running a 2D analysis where you cut a cross section here and you run the 3D will depend on the relative size of the two side of the rectangular, as well as all the soil conditions. So in any different situation, you will have different soil condition. Okay, so you can run for one model, you will get a certain percentage that might be 20-30% in difference when you, for example, and now I'm going to do this. So if you cut a section here,
we don't see the screen.
No, you don't see the screen. Oh, sorry.
No,
okay,
but
1 second.
If I to rephrase my question, does we have a bigger factor of safety when we make a problem 2D, does we have like a more conservative?
You have a more usually you have a more conservative, yes, because, and that's why I want to show you this. So if now can you see my screen?
Yeah.
Okay, so here, this was actually a very important aspect that I want to show you before, and then it crashed. So look, these are the sheet pile walls. So now I'm going to cut another section here. Okay. So this is the section of the sheet pile walls. And now I'm going to show here the no, sorry, I know it's not this. Okay. The bending moment of the sheet pile walls. And I go, yeah, so this is the last phase. Okay. So now here, if I investigate the sheet pile, I'm just plotting the bending moment. I can also plot the horizontal displacement. So the effect will be shown. So when you move up and down, so you will see that, look, this is the maximum bending moment you're getting. So if you move your section, so here, your section, your sheet pile walls is getting less force. So of course, if you instead will run of this example, 2D model, you will assume that 1 meter of this slice applies to the entire excavation. And of course, you will be then forced to design your sheet pile walls based on the maximum bending moment. And this bending moment is very likely lower than the one you would get with 2D, because this is also getting the effect of these corners. So, but this depends on geometry and is project based. So depending on the project, you will have a different percentage in your in the conservativeness you're getting.
Okay, thank you very much.
You're welcome.
חברים, עוד שאלות אחרונות, אם יש למישהו, ואנחנו נסיים את המפגש. עוד מישהו מעוניין לשאול? אוקיי, טוב. אז נראה לי שאנחנו נסיים לעכשיו. תודה לכל מי שהשתתף. Giuseppe, thank you very much for your time.
Thanks to all of you for attending the presentation, and I hope you found it fruitful.
Great.
Thank you.
Thank you
Thank you very much.
Very fruitful.